All right, so for those of you who joined us maybe recently, welcome to the very first junior session of the SPS seminar series. We are very excited to host two wonderful speakers today. The second speaker is Aras Selvi, who is a doctoral candidate at Imperial College Business School, supervised by Wolfram Wisman, who's in the audience today. So Aras is affiliated with the Computational Optimization Group and the Data Science Institute of Imperial College London, and he has recently completed his PhD research internships at the Alan Turing Institute as well as JP Morgan AI Research. Aras's research interests are the theory of data-driven decision-making under uncertainty, as well as its applications, especially in machine learning, privacy, and fairness. His recent works, he has been working on designing some optimal privacy mechanisms and developing efficient algorithms for robust machine learning, as well as approximating some hard decision-making problems via robust optimization. So today we will get a glimpse of what he's been up to most recently. So the floor is yours. Thank you very much, Raj, for joining us today.
Thank you very much for the introduction and for inviting me for the SPS seminar series. I will talk about Wasserstein machine learning, especially a paper that we completed recently with my collaborator Reza Belbasi, who is a PhD student at Imperial College Business School, and our advisor Wolfram Wisman, whose office I am borrowing right now to give this talk. So I hope you can see my second slide now. I will motivate the supervised learning setting here. So in general, in supervised learning, we talk about data points. And data points comprise features and some output variable. So the features here we model with X. X is a collection of mx many continuous values, and there's an associated output variable Y. Okay, so we will soon see that we will try to understand the relationship between X and Y. So we will try to predict Y. To be able to refer to the instance altogether with the features and label, I use the notation xi. So xi is X, Y. It's the feature label representation of the data point. But these data points are not fixed, but we rather think that they are random and they are coming from a true data generating distribution. Okay? So in supervised learning problem, we are trying to find a hypothesis that best explains the relationship between X and Y. So this hypothesis is modeled with H, which belongs in the hypothesis space capital H. So what we do is that we see some feature vector X, and we take it in H, and we make a prediction. So H of X is our prediction. And by looking at its difference between Y, we can assign a mismatch between them. How we assign this mismatch is actually via loss function. So a loss function estimates the mismatch between our prediction H of X and Y. So in the supervised learning setting, in the ideal case, we choose a function H or a hypothesis H that minimizes the expected loss between the prediction H of X and the true output Y, where the expectation is taken with respect to the true distribution P0. Okay. So this is what we motivated now. We have the objective function, which is expectation of the loss with respect to the true distribution. And you may ask, how can we design the hypothesis space? How can we fix the loss function L, as well as how can we solve this problem? So let me first answer the first two questions. Firstly, the answer of the first question, at least in this paper, is via linear models. Okay, so let's first start with the classification problems. For classification problems, Y takes values either -1 or +1. So this is binary classification. And because I just told you that we will be working with linear models, our H is a linear function of X. So what we do is that we fix betas, a vector of beta 0, which is an intercept, and beta x, which is like the variables corresponding to the features, and we take inner product between them. Okay. And in classification, the interpretation of this is that for a given feature vector X, we look at its signed distance from a hyperplane, which is defined by betas. And typically what we do is that if the sign is like positive, we say this point is a +1 point. So we label the point +1. And if it's on the negative side, we say this is like -1. So then we come up with loss functions that actually mimic this idea of looking at the sign. But because I just told you that in linear models, the function is parameterized by betas, the loss function, actually, if you can follow my cursor, can be modeled with betas as well. So we don't need to keep H of X, but rather there is a one-to-one correspondence with the betas and the loss we have. We can further have the univariate representation, which L is a univariate loss function. So it takes a single input, a single real value, and returns us the loss. And the input is the error. And the error in classification is the multiplication of the true label times our prediction. Okay? So let's see some examples. So the logistic loss is used in logistic regression, which is actually a convex function with Lipschitz constant of 1. A hinge loss is the loss function we use in support vector machines, which is a piecewise affine loss function. And the smooth hinge loss is a smooth approximation of the hinge loss, which also has a Lipschitz constant of 1. And these loss functions behave differently. They try to mimic the same 0-1 loss, but they all have different properties. So in general, this is a modeling choice. Or if we are doing some machine learning experiment, we experiment with different loss functions. In regression setting, h of x, again, is a linear function. But this time our understanding is not by looking at the sign of it, but rather we use the answer of h of x as our direct prediction of the output variable. And in this case, y is a real number. So it's not -1 versus 1, but it's a real number that we want to predict. So the univariate representation this time takes as input the difference between our prediction and the true output variable. Okay, so this is the error, how much we deviate from the true output variable, and we apply some univariate loss over that. Let's see some examples again. So the Huber loss is used in robust regression. So if you see the first line, it's the squared loss function that we are using in linear regression. But after a threshold of error, we apply a different function. Okay, so we are more robust to outliers. And this is, again, a convex function with Lipschitz constant of delta, delta being the threshold that I just discussed. And tau insensitive loss is the loss function we use in support vector regression, which resembles the support vector machine or the hinge loss. And the pinball loss is what we use in quantile regression. For example, if we want to estimate the 50% quantile or the median regression, we use the pinball loss, which in some cases is more robust compared to the linear regression. And again, these loss functions behave differently, and it's a modeling choice. But assume we fix one of these linear models as well as the loss function. Now, the question is that how do we solve this problem? And the main challenge is actually we don't know the true data generating distribution in practical settings. So if we knew the true distribution, then we would solve the problem on top. We would minimize the expected loss where expectation is taken with respect to the true distribution. But unfortunately, we don't know the true distribution because in reality, we only see a finite sample of the true distribution. So we see a collection of instances, psi n, which are independently sampled from the true data generating distribution. So traditionally, what we do is that we model an empirical distribution, which is trying to estimate the true distribution, because we don't see the true distribution, but we see samples out of it. So we generate this p hat n, or construct this variable, or this distribution, which is supported on the historical observation, and each observation has a 1/n equal mass. So in empirical risk minimization, we actually revisit the true risk minimization problem, but we change the distribution of the expectation with this empirical distribution. Okay? Now, there are great properties, statistical properties behind empirical risk minimization. So standard arguments say that if we see more and more data points, then empirical risk minimization converges to the true risk minimization problem. But unfortunately, in real life, data is scarce, and we cannot have infinitely many data points. And what happens is that in the finite data setting, we suffer from overfitting with empirical risk minimization. This has different names in different fields: error maximization effect of optimization, the optimism bias, or the optimizer's curse. Here, I'm actually visualizing a very simple experiment. So on the left-hand side, you see there are 4 points, and the blue points on the left can be regarded as -1 class, and the red points can be regarded as +1 class. And if I fit, it's like logistic regression, and if I visualize the decision boundary or the hyperplane, you see it's right in the middle. So it separates the blue class and red class from the middle as expected. But on the right-hand side, I place a blue point on the top right. What happens is that if I solve the logistic regression problem again, the hyperplane actually changes its shape quite a lot. It gets very close to the blue point on the top right. But you can see that the top right point, the blue point that I just added, is still being misclassified. So why did the hyperplane change this much? Because it's about the nature of the logistic loss. So it penalizes you more if you misclassify a point and it's further away from the decision boundary. So the model decides to get closer to it, even though it makes a mistake. So here we see that the impact of adding one point on the top right on the wrong side, maybe it's noise, maybe it's not, but it changes the shape of our function a lot. Okay, so we will see that we need to combat this to actually address overfitting. But I will come back to this experiment again. Now, traditionally, people came up with regularization method. So what regularization does is that we still solve empirical risk minimization. So on the left-hand side, you see this blue box, which is the objective function we had in empirical risk minimization. So we minimize the expected loss where expectation is taken with respect to the empirical distribution. So we didn't change anything about that expectation part, but we rather added a penalty term, which takes a positive constant C and multiplies that with a regularizer of our decision variables beta. And the regularization function is a function that is not a function of the data, but rather the function of our decisions. This is how regularization works. But philosophically, what regularization does is that it revisits empirical risk minimization and it revises how we explain the relationship in the empirical data set. So it doesn't change what we explain. We're still explaining something that happens in the empirical set. But when we do that, we need to be more mindful because our betas have a penalty in the objective function. But the way we fix the regularization term is in general ad hoc. And we ask, can we do something differently? This brings us to the distributional robust optimization literature. So the philosophy of distributional robust optimization says that we have overfitting because the empirical distribution that we estimated from the historical observations has a distance from the true distribution. So we have overfitting because of the statistical errors we make. So if W is a distance, and this is like a spoiler that soon I will be using Wasserstein distance, but for now, if we think W as a general distance between two probability distributions, then we must have a positive difference between the empirical distribution and the true distribution. And assume we know some epsilon that upper bounds this distance. Okay, so what DRO does is that we don't change how we explain the phenomena we see in the training set, but rather we revise what we explain. So actually, we are not minimizing the loss over the empirical distribution anymore, but rather a new distribution. And this distribution Q is a function of several things. So it's still a function of the empirical data set that we are seeing. It's a function of our decisions, as well as the distance metric that we take, and the epsilon that is modeling the radius of the distance between the true distribution and the empirical distribution. Okay, so this is a very compact representation. So let me show you the full problem. So in distribution robust optimization, we actually minimize decisions. So we mean like we optimize a variable beta in order to minimize the expected loss. But the expectation is with respect to this Q, another distribution, which is decided in a sub-problem inside. Okay, so let's break this down. So we see that any Q can be played by the sub-problem as long as its distance to the empirical distribution is upper bounded by epsilon. Okay, for example, we know that the true distribution is one of those distributions if this epsilon is really an upper bound. Okay, and we take expectation with respect to this worst case distribution. And nature, we say that the inner problem is played by a nature who chooses the Q by looking at our beta in order to maximize our loss. Okay, so that's why this has a natural game theoretical interpretation. But again, we talked about distances, but I didn't talk about which distance we are using. So this brings us to the Wasserstein distribution robust optimization. So the Wasserstein distance is written on my screen. So the distance between P and Q is found by solving a minimization problem. So this problem is overall, sorry, I cannot select this, but overall couplings of P and Q in order to minimize the expectation of a ground metric D. And this ground metric is defined on the space of the instances, okay, of the data points. So that's why we need to actually talk about the ground metric, which is very important in this problem. So the ground metric D in this setting is the feature labeled metric. So how do we measure the distance between two data points? So they both have features x and labels y. So we look at their distances and we add them. So when we check the distance between the features, we just take the norm of the difference between x and x prime. When we look at the distance between labels, this depends on what kind of problem we are working with. So if it's a classification problem, we look at whether they are the same or not. So if they are different, then this is one distance. But if they are the same, this is zero distance. But if it is regression, then we simply look at their difference. Okay? And therefore, a Wasserstein ball is a ball of distributions whose Wasserstein distances are not more than epsilon to the empirical distribution. Okay? Now, if we were to implement the distribution robust counterpart of logistic regression, you can see in the plot at the bottom that if I increase epsilon, so if I look at more and more worst case distributions, our solution becomes more robust in the sense that the hyperplane gets closer to the original shape on the top left. Okay. So there are many desirable properties that come with Wasserstein distribution robust optimization. So firstly, empirically, we see very good out-of-sample performance in machine learning experiments. But also the problem that I showed you admits tractable convex optimization reformulations with linearly many constraints. And we also have finite sample guarantees, which means that normally we don't know the epsilon that upper bounds the distance. But we can estimate it in a way that with very high confidence, we upper bound or we overestimate the true risk. Okay? And we are still asymptotically consistent. So similarly to the empirical problem, we are asymptotically consistent, but with high confidence, we overestimate the true risk. And there are sparse worst case distributions, which gives further business insight. So we can characterize the worst case distributions that are supported on at most linearly many atoms. And there is this famous regularization effect. So although the distribution robust optimization formulation is motivated very differently than the regularized regression problem, they are equivalent for a selection of regularizer function. But in this presentation so far, I assume that the features are numerical. But in machine learning, most of the data sets have at least one categorical feature. We actually checked the UCI data sets, and almost half of them have categorical features. And in the operations management literature, which we started from in this research idea, we see papers that are published very recently that come up with models that are using categorical features. Like in bike sharing, they use weather conditions, and medical appointment, they use like the marital status, and so on. Okay. So we need to define additional terms in order to acknowledge that an instance can have categorical features. So let's say we have k discrete features. Okay? So Z models the collection of k instances. And each instance, for example, the k1 discrete feature, by the way, I'm so sorry, there's a typo. It says numerical features, but I mean discrete features. So the k1, the first discrete feature has k1 many potential values, for example. Okay, this notation means that. And the Z of K1 is actually encoding these features with one hot encoding. Okay. Now we also need to have additional variables to optimize because we take a hyperplane, right? And the variables that correspond to the categorical variables are now modeled by beta of Z. Okay? And finally, remember that the feature label metric is defined by the distance between two instances. And now, because these instances also have categorical features, we add an additional term that simply counts the number of different categories between two instances. So this is the most natural way we can define distance on categorical features. Now, if I plug these back in my Wasserstein distribution robust optimization formulation, I will unfortunately have an NP hard problem. So in our paper, we show that even if you don't have any continuous features, and if you have a single training instance, the problem is still strongly NP hard. But the good news is that if the loss function is convex and Lipschitz or piecewise affine, so all the functions that we discussed before satisfy this, then the problem can be solved to delta accuracy in polynomial time. So I don't talk about how to solve it yet. So I'm just telling you that there exist solution methods that work in polynomial time. But on the other hand, again, unlike the DRO literature, Wasserstein DRO literature with continuous features, we show that the objective function, which we minimize in distribution robust optimization, does not admit an equivalent form with the empirical risk minimization plus a regularization function. Okay? So you cannot find any regularizer where the objective function we take in DRO problem is equivalent to a regularized counterpart. So this contradicts the literature in the case where all the features are continuous. And you may ask, then why don't we treat all categorical variables as if they are numerical? So to show what happens when we do so, we had a case study. So what we do is that we generate a case with a single binary feature, or not binary feature, sorry, single categorical feature, beta. And the true value is 1. We don't know that, but we holistically generate data that uses the logistic regression hypothesis, and they use the true coefficient to generate instances. And what we do is that we solve 3 problems. The first problem on the left-hand side, it's the green colored plot, is just the logistic regression problem. Okay, so the empirical risk minimization problem. And the blue colored part solves the mixed feature Wasserstein learning problem that we propose. And the red colored one treats the variable as continuous variable and solves the DRO counterpart. Okay? What we see here is that if you compare the position of these colors compared to the vertical line at the true coefficient 1, you see that the empirical risk minimization is unbiased. So it centers the true value and it converges to it over time if we have bigger and bigger data sets. On the other hand, the robust models, so the mixed feature and continuous feature models, are more conservative. So they approximate this coefficient from the bottom. But if you look at the red colored one, the continuous feature model, this is more conservative. So it's always under the blue curve. Okay? So the continuous feature model, treating variables continuously, is actually more conservative than what we propose. And the reasoning is perhaps empirically observed on the right-hand side. So on the right-hand side, what we do is that we plot how the worst case distributions look like. Okay? So if you look at, for example, the empirical distribution, there is no more worst case because there is a single distribution that we are talking about, and it's with blue shaded bars. Okay? So it's supported on points -1, -1, -1, +1, +1, -1, and 1, 1. Okay? If you look at the mixed feature model, the model that we are considering, the worst case problem that's played by the nature ends up at a distribution that looks like the red colored bars. Okay, so the messes are a bit different than the empirical distribution, but they are still supported on the points of -1 and +1 by definition. But the continuous feature model, because there is no support, we don't say that the features need to be either -1 or +1, has a mess on a point whose Z value is something very large, 15,000 or something. Because that's how regularization equivalence works in DRO with continuous features. So there is a point which is not supported on our data set, further away from the points that we observe, with very little mass. That mass goes smaller and smaller, whereas the point gets further away asymptotically. And that's how we end up at a regularizer. Okay? Now, next, you may ask that if the continuous feature model is more conservative, why don't you change the epsilon value? And we observe that actually naturally we end up at different problems as well. So what we do is that we simulate a case with 20 binary features, and we vary how many of those features we treat as they are. Okay? So for example, the axis with like 10 means that 10 of the categorical variables we treat as categorical, the remaining ones we treat as numerical. And we see that the more variables we treat as categorically, the errors become smaller and smaller over time. Okay? And finally, before I finish my presentation, I would like to show you the reformulation of the distribution robust optimization problem that we are working with under mixed feature. So on the left-hand side, you can see the classification problem, and on the right-hand side, you can see the regression problem. So I just want to discuss the complexity of this problem. So you can see that the objective functions are linear, and there are linearly many variables as well. The constraints are all convex because they use the original loss functions L of beta, and these are convex functions. And the constraints are also indexed for all n, which is linearly many. But the problem here is that the constraints are also indexed for every z that we can come up with, which means that any possible combination of categorical features can index our constraints. And there are exponentially many such constraints. So what we do is that we develop a cutting plane algorithm. This algorithm exploits the structure of linear models as well as some properties of distributional robust optimization. And we have finitely many iteration termination guarantee. And each iteration of finding a cutting plane actually works in polynomial time. So we implemented this algorithm in Julia by using the mosaic solver. And we observed that our experiments terminate very fast. So I would say that in real-life data sets, we didn't have a case that ran more than 1 hour. And we experimented on 15 real-life data sets from the UCR repository, and we observed that we outperform both the regularized learning problem, the nominal problem, as well as the DRO problem, where we treat all the variables as continuous. And I think I am now at my 25th minute, so I should wrap up. I will not talk about these details, the numerical details, because I left them for maybe Q&A in case you are wondering the numerical performance. And I will jump to the final slide. So this work is actually based on 2 papers. One appeared in NeurIPS 2022 that was focusing on the logistic regression case. And recently we have a journal version of this work where we extended our findings to more loss functions with more general guarantees, which is right now under second round review. And thank you very much for listening to me, and I'm happy to receive any questions you have.